Hello students, this is the second part of RSA. Now, let us look at this question. Prove the correctness of RSA. Basically, we have to show that RSA always works. Now, let us try showing that. We are given this equation, and let's try to interpret that equation first. D equals E inverse mod P minus 1 Q minus 1. This will imply that DE is congruent to 1 mod P minus 1 Q minus 1. Sure, but what else can we do with this? We can make it an inequality using the definition of modular arithmetic. DE is equal to 1, which is the remainder over here, 1 plus, and because we're in mod P minus 1 Q minus 1, we have K times P minus 1 Q minus 1. This is simply the definition of modular arithmetic. And to verify, you can simply take mod P minus 1 Q minus 1, and you'll see that they're completely equal. Now we have DE. So now let's look at the second equation. X to the power of ED is equal to X mod N. Now, notice that this part, we have E to the power of D. We have X to the power of E, then to the power of D. But remember, with exponents, we can simply multiply that because D is on the outside and it's not on top of E, right? So we have X ED. This is equal to XDE, obviously. And we know what DE is from this equation. So this is also equal to X to the power of 1 plus K P minus 1 Q minus 1, right? Now this is congruent to X mod N, which follows naturally from this equation. Now let's take this and let's interpret this. Remember what N is? N is PQ. But now let us separate the P's and the Q's, and let's see if this equation actually works. So we have X to the power 1 plus K P minus 1 Q minus 1 minus X is congruent to 0 mod P. Now if we pull one of the X's out, we have X to the power of K, X times X to the power of K P minus 1 Q minus 1 minus 1 is congruent to 0 mod P. Now notice that with Fermat's little theorem, this is always 0. This is always 1, not 0, sorry. So we have 1 minus 1 is equal to 0. So this will be X times 0 is congruent to 0 mod P. But what if X equals to 0 mod P? Well, if X equals to 0 mod P, it doesn't really matter to us because it's already multiplied by X in the front. So it'll still be 0. And this argument works for P, but it also works for Q, because Q is simply another prime. And Q minus 1 is also a factor of X's exponent here. So therefore, we know that this equation, X to the power of 1 plus K P minus 1 Q minus 1 minus X is congruent to 0 for both mod P and mod Q. Now, why does this tell us that this is also 0 mod PQ? And the reason is because P and Q are both primes. So we know that this over here is divisible by P and divisible by Q. But because the GCD of PQ is equal to 1, we know that that whole thing is divisible by P and Q. And it's also will therefore be divisible by PQ. And because it is divisible by PQ, by definition of modular arithmetic, we have that it is still congruent to 0 mod PQ. And therefore we are done proving that RSA works.